Okay, in the last video we talked about kind of the motivation for using numerical methods for finding roots of equations. And I said that there was two classes of numerical methods for finding roots. They were called bracketing methods, that was talked about in chapter 5 of the Shapra-Kennelly book, and open methods, which is talked about in chapter 6. And so in this video I'm going to talk about bracketing methods. And I'm going to introduce you to two different bracketing methods and kind of the basic idea behind bracketing methods. So this video is going to be about bracketing methods. Okay? So bracketing methods. Now, let's start off with a picture. Well, yeah, let's start off with a picture. So, if I have some function f of x, and I'm able to evaluate that function, but let's say I don't know exactly what the equation is of that function, so I don't know what it looks like. One way that I can find out what it looks like is I can actually start putting in values. So let's say I put in an x value here. I'm going to call this x lower, and it evaluates to be right here. Now, if you were trying to figure out where the roots of this function were, what might you do? Well, you could start plugging in other points. Say you plugged in a point here, and it was evaluated to this value, and then say you plugged in a point out here, and it evaluated to down here. Well, now you'd be probably pretty comfortable saying that, hey, I know that because the function evaluated to a positive value up here and then a negative value down here, I know if the function is continuous that it has to cross the x-axis between here somewhere. Between these 2 points, I can't guarantee that. So for example, the function might cross the x-axis and come back up like this, but it might also just do something like this instead. Okay? We have no idea. We can't guarantee that there are going to be roots in between these 2 points, but we can guarantee for sure that no matter what the function does, how crazy it is, it's got to cross the x-axis at least one point. Okay? It could cross the x-axis at any number of odd points. It could do something like this, but this is going to be an odd number of points. 1, 2, 3, 4, 5, 6, 7 points, right? If it was an even number of points, then this point would have to be up here. Alright? So we don't know if it's this case, if there's more than one root, but it's safe to say that the function has at least one root in this interval. And if this interval, I'm actually going to not call this XL, let's call this XL, and this X upper. This interval, defined by X lower to X upper, right here, if it's small enough, typically if you make this interval small enough, functions over small intervals, if they're continuous, tend to be pretty close to linear. So they tend to behave like something like this if the interval is small enough. It's not quite linear, but pretty close, approximately linear. So if our interval is small enough and our function isn't really crazy, it's probably safe to say that there's only one root. We can't guarantee it, but we can argue that it's probable at least. Okay? And so the way that we check for this condition is, what we have to do is multiply our function values at our two different points. So this is f of x lower, and this down here, right here, this is f of x upper, right? If they have opposing signs, so if one of them is positive and one of them is negative, then we know that their product, f of x lower times f of x upper, I don't need this p here, just xu, is going to be less than 0. If, for example, f of x upper was up here, then they'd both be positive, and this would be greater than 0. And if they were both negative, when you multiplied them together, their negatives would cancel each other and you'd have something above 0. So this condition that an interval bounds a root can be checked by checking this condition. So we use this condition, so I could say we use this condition, this inequality to check if the interval bounds a root. Now, if it does bound a root, then we can use some strategy to try and approximate that root. Okay? But all bracketing methods use this check to determine whether or not a interval bounds a root. So the first step in any bracketing algorithm, whoops, didn't mean to do that here. So step 1 in any bracketing algorithm is to use f of xl times f of x upper. Use this product to find an interval that brackets a root. Hence why they're called bracketing methods. Okay? So bracketing methods. So I'm going to talk to you about two different bracketing methods. The first bracketing method is called the bisection method. And you'll see why it's named that in just a second. Bisection method. So once we found an interval that brackets a root, so this is x, this is our function f of x that we're looking for the roots for. So let's say we've got, this is our interval x lower, x upper, and say our function, our interval is pretty small, so it's approximately linear between here. Okay, so now we can say this right here is f of x lower, and this right here is f of x upper. Okay? So, and this is our value for the root, the true value for the root. So what the bisection method does is it says, okay, I'm just going to guess the midpoint. I'm going to bisect this interval in half, and I'm going to use this as my approximation for the root. So x root. So in mathematical terms, we can say x root, we're going to set our approximation equal to x lower plus x upper divided by 2. This is the approximation equation for the bisection method. Now, depending on what this function looks like, you know, maybe if it looks something like this, or maybe it looked something like this. It might be far away from the midpoint. We're not sure. But if, you know, this is highly nonlinear, these two yellow cases, this green case is more linear. So the bisection method kind of assumes linear, you know, a linear fit between the two. And it also assumes that, I guess it doesn't assume linearity so much. What it just assumes is that this is the best possible guess. If you're going to repeat this guess over and over, you can be guaranteed that it'll converge to a root. So what I'm saying is okay, once I've chosen XR to be my approximation, the midpoint, well, I can get another approximation, hopefully a better approximation, by now checking. I've got two sub-intervals now. I'm going to write these. So now I have an interval, whoops. Now I have this interval right here, and the one next to it. This interval right here is XL, XR, and this one is XR, X upper. Alright, so what we need to do if we want to get if we want to apply the bisection method again and get a better answer, we need to find out which sub-interval, this one or this one, the true root is in. Well, now we have two intervals. The way that we can check to find out if an interval bounds a root is we can just use our test that we did before. So let's just check this one. So we could say if f of x lower times f of xr is less than 0, then we know it's in this side. And the way I've drawn this, that's going to be the case, because the true root, if this is the function we're trying to find the root, is in this interval. It's not in this interval. So I can see here the function value at xr is negative here. This right here is the function value at xr, right? So f of xl times f of xr is going to be less than 0. And then if I did f of xr times f of xu, that would be positive. So we would know it's not in this one. So not in this interval. But it is in this one right here, because this evaluates to true. So if that's true, what we want to do is we want to create a new interval where a new XL and X upper, and then apply the bisection method again. So if we're going to create a new one, our X lower is still going to be this lower bound, but now we're going to set X upper to be the midpoint of this previous interval. So if this is true, then what we're going to say is, and we know it's in the left side, then we're going to say set X upper equal to X root. Now if it was false and it was really in this interval here, then what we would want to say is else set X lower equal to XR. If that's the case, then we'll have created our new interval. So our new interval will now be XL to X upper, and we can now apply the bisection method again to get another approximation for the root, XR. So now our XR is going to be our new XL plus our new X upper divided by 2. And what that would do up here is it would divide this interval in half, right here, and it would set our new XR, so maybe call this XR2, this is XR1, that was for our first interval, and it's going to be set equal to this. Well, now we've got two subintervals, this interval right here and this interval right here. We can check which side the true root is on, make this a new interval, and then divide this in half. And now you see we're getting closer and closer to the root as we successively divide our intervals in half, getting smaller and smaller intervals. So this, have a little animation here. So showing you the bisection method. So starting out we have XL1 and XU1 right here, XL1 and XU1, and here's our approximation for the bisection root for this first interval. And then all we do is we determine that the real root is over on this side. We come up with a new interval, XL2, XU2, and here's our root, XR2. Alright, so I just kind of want to write down the general steps of this algorithm so that we can actually implement it in computer code. Okay, so the general steps is you have to have the first step, of course, which is the first step of all bracketing methods. So assume XL, the interval XL, XR, brackets a root. Brackets a root. And we can do that by employing our test. So, such that f of XL times f of X upper is less than 0. Okay? So we're going to assume initially we find a value for XL and XR such that this is true. So that's the first step. And then what we're going to do, the second step, is we're just going to use the bisection method to approximate the root. So we're going to approximate the root with this equation. X root is equal to the midpoint, which is just X lower plus X upper divided by 2. Now once we've done that, we've divided our, we've bisected our interval, so now we want to find which subinterval contains the true root. And we do this by performing the following check. We say if f of x lower times f of x root is less than 0, then we know that it's the left interval. So I'm just going to put I'm almost writing MATLAB code here, putting this percent sign to say this is a comment. So we know this is in the left interval. Then what we want to do is update our values of XL and X upper. We want to keep our value for XL, so we won't change that. But we're going to change X upper to be equal to XR. And if it's not true, then we know it's in the right side. Okay, this is the case where we have this is the case where f of xr times f of xu is less than 0. Okay. Then we want to set x lower equal to xr. And then we will be done. And in MATLAB code, we actually have an end here to end this if statement, right? Okay. So then that's that step, step 3. So find which subinterval contains the true root and create our new interval. So now we've created our new interval. The third, is that step 3 or 2? I can't remember. That was step 3. Okay, so the fourth step then is, fourth step is just to repeat steps 2 and 3 iteratively. I'm not sure if I spelled that right. Until your root approximation is good enough. That's the algorithm. Pretty basic. Really just 4 simple steps that you should be able to turn into code. Alright, now let's talk about good enough here. So what constitutes good enough? So typically the way we determine good enough is we want to quantitatively measure the error. So we can calculate the percent relative approximate error. We talked about this in a previous video. This is defined as, I'm going to use absolute values. So the x root, the new value for the root, minus the previous value for our root. So I'm going to call this old value, all divided by our new value times 100%. And this gives us an idea of how bad the error is. So we can calculate this, and it's going to spit out a percent, an approximate relative error. So what we might provide is when the user wants to use this algorithm to find a root, we have some program that's been written in MATLAB to implement the algorithm, and you're going to pass that program what we call a stopping criterion, some percent value that you say keep running and finding better approximations for the root until your approximate error is less than this stopping error. So we'll say go until, so do step 4, repeat over and over, go until your approximate error is less than your stopping error, what we provide. So we might say go until this is less than 0.1%, something like that. Alright, this is the basic algorithm for bisection. There's one other algorithm that I'm going to talk about, bracketing method, called the false position method, but I will talk about that one in another video. False position method. And after I've showed you in the other video the false position method algorithm, which is almost exactly like bisection except for one thing, I'll do a video where I implement some examples in code. So, alright, that's it for this video.